Welcome back, ladies and gentlemen. This is our second video on trends. The previous one is about atomic radius. So just quickly review atomic radius real quick here. We said that as we go down a group, the atom gets bigger. Okay, this is a pattern going down because of added energy levels or added energy electron shells, or we just simple terms, it is adding rings. And as we go left to right, it decreases in size. Gets smaller and smaller because of the stronger effective nuclear charge, because we're adding more electrons in there. So we should have the same number of rings going left to right, the same number of energy level going left to right on the same row. So the shielding is the same, but we're increasing the number of protons, so therefore the effective nuclear charge is slightly stronger, pulling the electrons closer, making the atom smaller as we go left to right. Okay, so we'll close that. Today we're going to hit on two more trends: ionization energy. So ionization energy, by the definition of this summary here, it is the energy required to remove the highest energy level electron from a neutral atom. So simply put, is the energy required to remove an electron. Okay, so we'll get down to the notes here. Energy required to remove an electron from a neutral atom, so the outermost electron basically. And the trend for this, so what's the pattern as we go down the group? As we go down a group, it decreases. So ionization energy, we're going to use ice cream, for ice cream here, to help you remember. Okay, and it falls over to the left. It gets bigger as we go from left to right. Sorry, it falls over to the right. So left to right, increase left to right, and decrease down the group. Oftentimes, you'll see it presented as which direction of increase, and direction of increase, as you see here, it increases going up, and it increases going to the right. So it increases up and to the right. So the one further top and to the right is going to be more electronegative. Okay, the ones further more electronegative are up on top and to here. But using the ice cream method, or ice cream as to help you remember, you can always draw it like that, and you can get an idea. So it's increasing that direction. Absolutely increasing that direction, up and to the right. The reason for that, ladies and gentlemen, as you read here, across a period, effective nuclear charge increases as electron shielding remains constant. This pulls the electron cloud closer to the nucleus, strengthening the nuclear attraction to the outermost electron, and is more difficult to remove. So let me put it in basic, simple terms to help us remember this as left to right. So left to right, the atom gets smaller because of a stronger effective nuclear charge, right? So we already knowing that, so we'll cut that part out and we'll just simplify it as, so basically as atom gets smaller left to right, atoms get smaller due to stronger effective nuclear charge. It's pulling, it's holding to electrons a little stronger. The attraction is stronger. Attraction to electron. Electron is stronger. So requires more energy to remove. I'm sorry, my handwriting is a mess. Requires more energy to remove electron. Okay, sorry, you could summarize that as a little bit more if you want. Like the first part, you can put that stronger effective nuclear charge, attraction to electron is stronger, therefore it requires more energy to remove that electron. Okay? And so as we go to reason for decrease, it decreases going down, because remember, as we go down, the atom gets bigger in size. The size gets bigger. That's not very clear. The size gets bigger, right? The radius gets bigger. So that's opposite for ionization energy. Remember, the larger atoms, so as we go down, the effective nuclear charge decrease because of shielding. Okay, so larger atoms have lower which is nuclear attraction, thus requiring less energy to remove electron. That's fine. Writing is just like that is really hard to fix now. Larger atoms have lower nuclear attraction. Oops. Large atoms have lower nuclear attraction, requiring less energy to remove. So as we go down, it gets lower and lower because of the atoms increasing in size. Further from the nucleus, easier to remove. So it's far from the nucleus, it's easier to remove. So the concept is quite simple here. Let me illustrate that with an example here. So we have a small atom with, let's say, 2 rings, this electron, and then a bigger atom, proton in the middle, bigger atom with electrons on the outside. Okay, so which one requires less energy? Which one requires less energy to remove? Which one's easier to remove? So this guy over here is easier to remove because because it's further away. The attraction to the nucleus is weaker. So attraction is weaker. So therefore it's easier to remove. Lower ionization energy, IE. Okay? And the smaller one here, it's closer, so it's holding onto it tighter, right? It's holding onto it tighter, so it's harder to remove. So then higher ionization energy needed. So because the attraction is stronger. So simple. So to summarize, it really is smaller atom will have higher ionization energy than larger atoms. I'm sorry. Word salad today. So that's that. And so as we practice, if you look at the practice words here, right? OS and GE, you mark it with a marker. O, S, and GE. We put them in order of increasing. Increasing means from smallest to largest. Lowest to highest. So ionization energy, we want to focus on lowest to highest. So the lowest one would be the biggest atom in size. So germanium, it's going to be the lowest, and then sulfur, and then oxygen. Also remember the ice cream cone. Draw the periodic table if you need, and give you an idea of ice cream cone then, right? So on the bottom, the lower it is, the lower the ionization energy. So we got GE, S, and O on that one. So here goes GE, S, and O. Okay. Moving over here, Li, O, and Ca. Li, O, and Ca. Li, O, and Ca. Right. So Ca is going to be our lowest ionization energy because it's lower in the periodic table. But now you have 2 of them on the same level, on the first level. So these 2 are on the first level here, on the same level. Sorry, not first level. So Li is a bigger atom, so Li will have a lower ionization energy. It's a bigger atom in terms of size, in terms of radius. So that means it has a slow, lower ionization energy. So Ca, Li, and O on that one. Okay. So you practice on some of these. Practice on these. Put them in order, and then rate from decreasing. So this increasing is from low to high. Decreasing is from high to low. So be familiar with both ways. Okay. All right. So pause the video, finish this part, and then hop on to the next part of electronegativity. Electronegativity, ladies and gentlemen, is the measure of ability of an atom in a bond to attract electron to itself. Which is the most attractive? So ability to attract electrons. The explanation here is quite long, so I'm going to put it in very simple terms so that we can understand it a little better. Autofocus, come on. Okay, it's trying to focus. Oh, there's a marker in the way. Okay, electronegativity is ability to attract electrons. Okay, simple as that. And it's going to be the same trend as your ionization energy, so you can draw the ice cream cone for both of them. Okay, ice cream cone is for electronegativity and ionization energy. The snowman was for the size, for the radius. So left to right, increase. Top to bottom, decrease. Okay. The reason for that is if you have an atom. Think of this: if you have a small atom, and then you have a bigger atom, so it's all related to the radius, right? Because the radius tells you how far the nuclear attraction is. It's the nucleus that's trying to attract. There's an electron out here. There's an electron out here. So which one is closer? The attraction is toward the nucleus. The smaller one, the nuclear attraction is stronger because it's closer to the electron outside. The nucleus is going to attract it a little better. Closer means less shielding. And again, shielding is basically these rings are blocking, are reducing these rings here, this electron cloud, this electron shells here, are reducing the amount of attraction to the nucleus. So there's more shielding on the bigger atoms. So there's a weaker attraction for the bigger atoms, right? So weaker attraction for bigger atoms because they're far. So if you're trying to attract something, you're trying to pull something in, it's easier if they're closer, right? For sure, it's easier if they're closer. And so your nucleus is going to pull the smaller atom is going to pull the electrons in a lot easier. So higher ionization energy for the smaller atoms, and lower ionization. No, sorry. Electronegativity. They're actually opposite. One is to remove electron, and electronegativity is to attract an electron. So, back to our definitions and our notes and the reasons. The reason for increase left to right is smaller atoms. Smaller atoms have nucleus closer to surrounding the electron. Let's just say that, surrounding electron. So therefore it's a stronger, more attractive, higher attractive force, higher attraction. Okay? It could be put in many different ways. That's what comes to my mind right now in terms of putting it to as simple as we can on the reason. Okay? As we go down, decreases as we down because the size of the atom. Remember, the size of the atom gets bigger as we go down. The radius. Okay? Talking about the radius here. As we go down, the radius gets bigger. So then, the larger atoms, 1T, atoms has larger have lower nuclear attraction to outer electrons because it's further. The distance is too far out. Pretty simple concept there. So as long as you know the radius, guys, bigger the atom, as long as you know it's bigger in size, lower in ionization energy, and lower in electronegativity. Okay, so let us practice here. We have Na, K, and Ne right below the table. Na, K, and Ne. So technically speaking, noble gases aren't going to have electronegativity because they're already full. They're not going to attract anybody else. So we disregard that column when it comes to electronegativity. So the most electronegative element on the periodic table is actually fluorine. But for the sake of applying the trend, let's just assume that, for sake of applying that, even though this is not a good question to include neon or noble gases in there, but since it's on the paper, let's just follow the trend and apply it, okay? So the lowest one is from increasing, so the lowest one is K. So K would be the first one. And then the second one is Na because A is a bigger atom, and Ne would be the highest ionization electronegativity. Okay, K, Na, and Ne. So bigger atom, lowest electronegativity. All right. So practice on these. That's really all the notes there is to it, and my 15-minute time limit here is out on this video. So that's really all I can do. Goodness, look at my handwriting is so bad. Sorry, guys.